here. So our session is being recorded. And what I like to do sometimes, I mean, of course, I refer to the book and definitions and things, but sometimes I like to just go right to an example because the example will help illuminate you on ideas that are talked about in the book. So multivariable calculus is calculus in three-dimensional space. So you're used to two-dimensional space. You're used to doing calculus, where you have an x and a y axis, and you're doing calculus in two-dimensional space. But planes, for instance, airplanes don't fly in two-dimensional space. So as engineers and scientists, you need to be able to work with three-dimensional space. So section 9.1 introduces three-dimensional coordinate systems. And I have a nice little example that we're going to work out. So let me give you a moment to copy the example down. I'm going to pace myself, assuming you're copying examples down. How many feel that it helps to copy an example down? How many that writing is thinking? How many of you take notes in class? And, all right, Deodeth does, and Ryan and Eric. Wow, a lot of people. Ryan and Robin, and that's great. That's great. That is wonderful. And I'm learning people's names: Binyam and Dan and Christopher and Naima and Eric and John. And all right, Robin. I know a lot of you, some of you already. All right, so let me give you a moment to copy this example down, and then we'll talk about it. Now we're dealing in three-dimensional coordinate systems. And, you know, here's a coordinate, 3, 7, -5. So the first value is the x coordinate, 3 is the value of x, 7 is the value of y. So x and y are exactly as you're used to seeing. And then we have this third coordinate, which is your z coordinate. And z coordinate is for going up and down. That's what the z coordinate is. So if we were to draw the coordinate system, you know, that's your z-axis, that's your y-axis, and that's your x-axis. I can label it here. Z, y, and x. And that's standard for this textbook. So please use that. Please use that, even if, you know, maybe you've seen it in another class, different. We want to use this orientation for this class. And of course, you know, we have to worry about when z is negative, right? So to do that, we just you know, we can extend that down. It's dashed. You understand? Well, hold on. I can do it. Wait, I got an idea. Hold on. Hold on here. I didn't like that, did it? Hold on. All right, I'll do it. I'll have to do it by hand. So when the axis takes on negative values, we put dashes. And then right here in the center is the origin. Okay, right there in the center. Okay, so the XY plane would be the plane that contains the XY axes. The YZ plane would contain the YZ axes, and the XZ plane would contain the X and Z axis. And so these three axes, the X, Y, and Z axis, together separate space into how many corners or octants. How many octants are there? That's right, Christian, there are 8. That's right, Benjamin, 8 octants. Okay, the XYZ axis splits space up into 8 octants. 4 above the XY plane and 4 octants below the XY plane. And you have 3 planes. So you're used to a distance formula, right? I mean, you've seen a distance formula. I'll write it down for you. Okay, I'll write it down for you. But one moment. Hold on, class. One moment. Okay, so we're just kind of having I mean, I could bring up the ebook and, you know, have, but we're just kind of, I think examples help illustrate, help get you thinking. Let's put it that way. Okay, so distance between 2 points. Okay, here's what you're used to seeing. How many of you does this ring a bell? How many of you remember that? Maybe it's even been pre-calculus since you've seen that, but sure, that's the distance between 2 points in the XY plane. But now we're talking about 2 points in three-dimensional space. So what might be natural to add here? What might be natural?
Z squared.
That's right, very good. Z2 minus Z1 squared. Okay, and that's how we find distance in three-dimensional space. Okay. So, sometimes when people have a formula, that's right, Binyam, same principle as adding a dimension. That's right. So in linear algebra, in Math 284, we learn about the distance formula. We can find the distance between 2 points in any dimensional space we want, and it's just an extension of well, it's based off of vectors, but this, in calculus 3, we're sticking to three-dimensional space, and that's the formula. But what would I need if I have the point 37 negative 5, 37 negative 5. If I want to plot 37 negative 5, I mean let's plot that first. So, and I'm going to go to the next page has like the full solution worked out, but I just kind of want to talk about plotting 37 negative 5 on my little picture here. So along the x-axis, do I go forward or backward if the x coordinate is 3? Would I move forward 3 units or backward 3 units? That's right, forward 3 units. So say that's forward 3 units. And then the 7, okay, along the y-axis, do I go 7 units to the right or 7 units to the left, since I have a positive 7? That's right, very good. You move to the right 7 units. So, I could like put a 7 here, and, I could just kind of move over 7 units, maybe stop there. Okay, but now I got to do the negative 5 for the z coordinate. So do I go up 5 units or down 5 units? You go down, good. So, I can go down 5 units. Maybe negative 5 is here, but you have to kind of adjust your perspective. So maybe right there, I'll put a big dot, and there is 3, 7, negative 5. So using Cartesian coordinates, you can locate any point in three-dimensional space. But just like you learned in calculus 2, you learned about polar coordinates. In calculus 3, we have, in addition to Cartesian coordinates, we have cylindrical coordinates and spherical coordinates. We have other coordinate systems that we're going to be using. But for now, we're going to keep it simple and stick with Cartesian coordinates. So, I see that 3, 7, negative 5 is located in that lower octant. And I want to find the distance from 3, 7, -5 to the xy plane. Okay, so that distance, I mean, like based on the picture, can you highlight that distance? Can maybe somebody write on the picture to sort of illustrate illustrate what that distance is? The distance, like for part A here, the distance from 3, 7, -5 to the xy plane. Ah, okay, somebody did that. Good, good. That's absolutely right. Thank you. That's absolutely right. That's going to be this distance right here. And maybe, let's see here. I like to use colors that are nice to see. Maybe I'll put it in black. There it is. Well, what is that distance? 5 units. 5 units. Absolutely. That's the z distance. So I didn't really need to use the distance formula. I mean, I could have used the distance formula. I could have. Okay. In fact, what I would have done is I would have said, okay, well, this coordinate here is 3. What's that coordinate going to be there? 3, comma.
370.
Good. 370. Good, Christopher. Good, Ryan. Yeah, and I could, you know, plug those coordinates in the distance formula to get the distance, but isn't it easier just to intuitively see it's 5? So what I think, yeah, it's quicker. So what I think I'd like you to do, I mean, I could show the solution, but do you think maybe you could spend maybe 5 minutes trying to figure out what, well, what, see in the next couple minutes if you can figure out the answers to B and C. Maybe you won't need the distance formula for that. Maybe you can intuitively get it. Let's see if you can figure out the answers for B and C. That's the distance that my red point here, right here, is from the YZ plane. And that's just going to be the Y distance. Oh, no, that's going to be, sorry, let me say this right again. The YZ plane, yeah, that's going to be the X distance. And then the distance to the XZ plane would be what? Well, think on it. Think on it. And let me know if you have any questions, okay? If anybody's uncomfortable. Let's see, Eric says, when calculating distance from a plane, it's easy just to take the value of the point not in that plane. Yeah, well, I just look at it as like just sort of figuring out what the distance is. But let's see here. Eric, I'm not quite sure. I think I kind of know what you're saying, but I'm not quite sure I'm quite there yet. Do you have the answer for C? 7 is right. So Christopher, you're doing it right. Nema and Binyam, okay, the y distance. Okay. Now for these other three, for D, E, and F, that's a little more effort. But let me go ahead to the next page. Let me go to the next page here. And what I've done, I'll tell you what, see if you can, well, no, I know what I want to do. Hold on. I want to go back. Oh, man. Well, you wrote the picture. See if you can figure out what D is. Okay, see if you can figure out what D is. And I want to go to the solution. I won't show D. And don't look at D, okay? But I've just drawn, you know, what I've done is, like from the point 37 negative 5, the distance to the x-axis, okay, would just be this distance.
You can just draw triangles with the other two values as the sides and solve
Exactly
for the
right.
hypotenuse.
That's exactly right. That's exactly right, Christopher. And Binyam, and Eric, you're right. That's the square root of 74. You can use the Pythagorean theorem. Exactly, because you have a right triangle here. You have a right triangle right here. That's a right triangle. Now, if anybody's uncomfortable, just let me know. You know, let me know. I like to kind of have, when I do examples, I like good participation and active thinking. You know, that's good participation. All right, we'll try then E and D. See what you can get for E and D. Take a moment here. Gentlemen, and that is correct. That is correct. Ryan Trask, that's right. So for E, the distance from that coordinate to the y-axis is square root of 34. And for F, the distance from the coordinate, that coordinate 37 negative 5 to the z-axis is square root of 58. And what I've done is I've actually used the distance formulas just so you could, just so, you know, you don't, I mean, you can get it using Pythagorean theorem, but I just did it with the distance formula just so you could see the distance formula being used. Well, Binyam, you know, the graph is clean. I use something called a ruler. Okay, how many have rulers maybe collecting dust in their drawers at home, or like a, you know, a protractor has a thing to measure angles and a straight edge. Okay, so got to start getting that out now. It'll help a lot. There you go. There you go. You know, I've had in the past at times when I draw sloppy drawings, I end up saying, man, I need a nice drawing, you know, to help me. And okay.
Engineering classes help.
Oh, yeah, yeah, yeah.
Lots of rulers and graph paper.
My PhD's in mathematical statistics, and so my wheelhouse, so to speak, is the statistics area, and of course math. But indeed, certainly like architecture, engineering, sure, sure. This is all used in calculus, in statistics, calculus 3. You need it. All right. Well, if we're good with this, I'd like to move to the next example. Are there any questions on this problem? All right, and I'm trying to pace myself. May I move to the next example? We're good? All right. Let's move on. Okay, yet another example. Okay, take a moment to copy this example down. Okay, so, all right. So here we have an equation, y equals 2x. And normally when you see y equals 2x, what do you think of? What figure do you think of?
A line.
A line, absolutely. But now we're working in 3 dimensions, 3-dimensional space. So y equals 2x. It can't be a line. It can't be a line. It has to be some kind of surface. It has to be some kind of surface. It can't be a line, but still it has. I mean, it has the property of a line in a sense, but I mean, let's see here if I can. So what's missing from the equation? What's missing from the equation? Z. Okay, so what's that tell us about Z? Eric says there are no Z values, but in other words, we're not saying anything about Z. That means, so think back to, okay, think back to, now this is an aside here, but think back to calculus 1 and 2, okay? Okay, now let's think, you have like an x-axis and a y-axis. So this is an aside here, but you have, an x-axis and a y-axis. And let's say you have, the equation y equals 2. Okay, we know that y equals 2 is, in two-dimensional space, y equals 2 is a horizontal line, right? It's a horizontal line. And of course, it's going to pass through the y-axis at 0, 2. Now, y equals 2, that equation, what variable doesn't it tell you anything about? Y equals 2. It doesn't say anything about x. Yet when we graph, very good, when we graph y equals 2, y always equals 2, but that's for all values of x. That's right, for all values of x. In other words, x has infinite values. So could we make a similar analogy for y equals 2x in three-dimensional space? In three-dimensional space, y equals 2x. What if we were to take a, what could z be then for y equals 2x in three-dimensional space? Z can be how many values?
Any value, all value.
Any value. Any value, that's right. So picture taking the line y equals 2x and moving it up any z value, moving it down any z value. What are you going to trace out in three-dimensional space? What's going to be traced out? That's good, Eric, good, Christian. That's going to make a plane. That's right, Binyam. And that's what happens. You have a plane. Y equals 2x is a plane in three-dimensional space. So you see what I've done here, of course it just isn't, we would like to draw the plane reasonably. Okay, so what I do is I say, okay, well, I know y equals 2x would connect the origin, this O here, is the origin, right? And so it's going to connect the origin to the point 1, 2, 0. That O there is the origin, right? All right, so like y equals 2 times x, so 2 times 1 is 2. 2 times 1 is 2 times 1 is 2. So the point 1, 2, 0 would satisfy that plane because 2 equals 2 times 1. And imagine taking that line. Imagine taking that line and lifting it up a distance, say, of 1. Imagine taking the line and lifting it up a distance of 2. you know, and lifting it up any value you want, you're going to form a plane. And actually, I didn't draw the entire plane because I figured it would be hard to picture it. But you know, the plane goes, you know, back, you know, and it goes like this, and it goes down too. You know, I didn't draw the below the XY axis. I didn't draw the plane, but you know, I'm just trying to. I think you see what I'm getting at here. Yeah, kind of fun, isn't it? How many of you were getting tired of the two-dimensional coordinate system? Of course, if you took linear algebra, you wouldn't be. but you know, if you're from Calc 2, you know, Calc 1, hey, you know. So yeah, you know. And you know, you can space things. You can like dash things a little bit to helps with the perspective. But yeah, there's a plane. So what happens is in your homework, in your section you know 9.1 exercises, your first set of exercises that are due this Thursday, you're going to have problems like these kind of problems are usually multiple choice. And you want to be careful when you answer multiple choice problems because there are limited number of tries on those. Just because, you know, I don't want you to guess and get the answer right. So like, for instance, if your multiple choice question, if it had four choices, well, you would get 2 tries, okay? Because anything more and you'd have you could have a better than 50% chance of guessing. If you had a multiple choice question and there were only 2 choices, how many tries would you get? If there were just 2 choices, yeah, you get 1. So you know. But at any rate, are there any questions on this one? Nah, Binyam, not 4. All right. Why don't we do one? Why don't we do one more? Are we ready to go to the next one? Okay. All right. Take a moment on this here. And while you're doing that, I'm just going to ask, Naima, can you hear me okay? Good. Were you able, is WebAssign working for you all right? Okay, so you were able to register okay? All right, very good, very good. Okay, all right. And let me see, let's see, is Derek here? Derek Jones? Okay, all right. So okay, so now normally when you see something like this, I mean, like if you had, for instance, And now in two-dimensional space, let's take something very simple. If you had x squared plus y squared equals 9, yeah, that's right, William. You'd think of a circle. That's right, Ryan. That would be a circle with radius 3. And, you know, x squared plus y plus z squared equals 9. You know, I have a z instead of a y. But that could be a circle in 2 dimensions. If you had an xz plane, that would be a circle. But, of course, in 3-dimensional space, x squared plus z squared equals 9 can't be that can't be a circle.
Cylinder.
What do you think it is, Christopher?
A cylinder.
You know, that's absolutely correct. It's a cylinder of infinite length, just like the plane is of infinite, you know, goes infinite length, so to speak. It's a cylinder that goes forever. But what axis goes through this cylinder? You know, what axis?
The y-axis.
That's right. It would be the y-axis.
Because it exists for all y values.
That's right. That's right. And Christian, very good. And Christopher, very good. So if we go to look at a little picture here, I've drawn that cylinder. So what I did was in the xz plane, I drew a circle that satisfied this equation. But since y can be any value, we can shift the circle along the y-axis to the left of the origin and to the right of the origin. And if we put all those circles together, you know, think of a bunch of circles here. All the circles obey this equation. The x and z coordinates have to obey x squared plus z squared equals 9. If you know, just shift the circle along the y-axis, you get a cylinder. Okay, are there any questions on that? All right, let me give you a moment to copy it down. Okay. And I want to point one more example out. I think I'll probably go into the ebook for this one. I like to pull my examples from varieties of sources, but the examples that I use are, you know, the book has good examples, but sometimes I use different examples just to give you a wider variety of examples which you can refer to. But I'd like to go into the ebook. One moment. Okay, may I move forward? Are we good on this one, this example? All right, Christian. All right, everybody. Everybody has it copied okay. Oh, Robin pointed an error here. This coordinate here, thank you, Robin. This coordinate here should be 0, 0, -3. Good catch, Robin. Thank you. So please correct that in your notes. This coordinate here is not 0, -3, 0. It's 0, 0, -3. I'll fix my notes on that too. Let me do that right now, lest I forget. Okay, so that being said, let's proceed on here and go into the ebook. Okay, and we are going to go to chapter 9. See, the ebook has Calc 1, Calc 2, and Calculus 3. Chapter 9. It's kind of nice. You can review things if you need to. I wanted to go to example 6 here. Wait, hold on. Where am I? Wait, I want to be in section 9.1. Here we go. We're going to talk about vectors, but not yet. Okay, so the equation of a sphere is basically an extension of the equation of a circle. Okay, that's the equation of a sphere. And you know, like with circles, they would give you a circle, equation of a circle, and you'd have to rewrite it to find its center and radius. You'd have to complete the square. Well, with finding the center and radius of a sphere, you have to do a similar thing. So in example 6 here, one moment. Are you seeing this okay? Do I need to bring this? Hold on. I think, I don't know why it isn't there. Hold on, class. Man, hold on. Let me go back in. Where? Okay, good. So, you know, you have to complete the square, all right, and get the circle in its standard form. And you've done this kind of thing with circles before, so I'm not worried about that. But I just wanted to bring it to your attention. The book has, you know, good examples to look at. Are there any questions on this? Okay, well, I'm going to stop the recording.